Okay. We are completing our journey of magnetostatics. In fact, we kind of left the world of magnetostatics, although I still kind of group these lectures together, when we started to talk about Faraday's law, which is changing magnetic flux will circulate voltage around that flux, opposite the direction that the change is. So one way to kind of think about inductance, what we did is we actually calculated the inductance for a coaxial cable. Know that coaxial cable. Because that's a very useful thing to do. We did the capacitance already, and now you actually can see how to set up any type of transmission line problem to calculate the inductance and the capacitance. So it's nice to see an application for all these integrals that we've been hammering away at. And one way to think about inductance is a sort of current momentum, right? If I have a wire with current on it, that has a magnetic field around it. If this is a magnetostatic current, it will have, let's see, coming out of the board up top, and going into the board at the bottom, a la the right-hand rule. And if this is a DC current, there's a static magnetic field there that sets up around the wire, and it represents a stored energy. If you try to shut this thing down, if you try to turn off the spigot, so to speak, and change the current, the magnetic field is going to start to shrink. Thus, if I were to make a little flux integral here, magnetic field is coming out of the board. The derivative of that flux is now negative, which means if I'm, according to my right-handed convention, my flux is negative. My change in flux. But of course, Faraday's law says there's a negative sign in there anyway. So that will incite circulating voltage around the path here. So this is starting to shrink. If I try to choke off the current, there's a negative sign in here anyway. And the result is that the E field will circulate up here with this polarity around this path. So I just draw a little integral, and I see an E field that wants to circulate around here if I try to shut off the current. And likewise, I can do the same down here, just the polarity changes so that it's clockwise instead of counterclockwise. And of course, what does that mean? Well, that means there's going to be a voltage drop from here to here, which is going to try to push the current back up to its original levels. And so it's interesting that when charge is flowing in unison, it has a sort of momentum to it. And that's really what the inductance represents, and a charge momentum. The current will try to keep doing what it was doing. It resists change. Yeah?
So the direction of the current is dependent on how the field circulates, I guess?
That's right.
Okay.
Yep.
Could you explain again why that's negative?
Okay, so if the caveat here was, or the given was, I've got a current that's DC, and I try to turn it off, right? I try to shrink it. You know, maybe I have a battery here and I start to lower the voltage or something. Then the B field, the magnetic field that circulates around this wire, will also try to shrink, right? Because B field is always proportional to I via the related to the inductance. Now, if that B field starts to shrink, the derivative is going to be negative with respect to time. And when I put a negative sign there, then it's going to be positive. So via the right-hand rule, I will have positive E field circulating that way for the B field pointing out of the thing. And then for the B field pointing in here, I'd have positive E field this way.
So this negative sign is not an indication of polarity, it's more so an indication of the reducing side.
Yeah. Yeah, well, the reducing amplitude of the B field makes this part negative, and then the basic fundamental Faraday's law has a negative sign in front of it. So the result is if I try to shrink this current, I get a positive right-hand circulation of E field in either direction. And of course, we know that if E field is pointing down along this wire, that's going to make a voltage drop from here to here. And that means, if this was an ohmic wire, I'm going to push current. I'm going to push more current in that direction. So you can see that there's a sort of built-in momentum to this Faraday's law equation that keeps wanting to push the current along. It doesn't like current to stop. And that's sort of the nature of inductance. And of course, the inductance increases as you take a wire and wrap it into coils, where the magnetic field now doubles back in on itself. And it really has a lot of current momentum, so to speak. So that was kind of the talk last time. We introduced the definition of inductance, and then we used it to come up with the basic circuit theory relationship. V is equal to L di dt. What we're going to do today is actually kind of fun. We're going to talk about mutual inductance, because here the current affects itself. Self-inductance is current affecting itself and resisting change. Because current, like the charges that constitute current, essentially cooperate with each other and impart a certain momentum to one another. It turns out that you can actually use this effect at distance. And if there's another wire or metal structure up here, you can induce currents at a distance from there as well. By coupling the systems. And that's really what today's lecture is going to be about. So in your notes, let's put the title Mutual Inductance. Mutual inductance. And to start out with, I'm actually going to review the homework problem that you turned in Tuesday, or at least my solution to the homework problem that I put online. And do you remember what you did for one of your homework problems? You had a square of current traveling in a square, not unlike this square, right? Everybody see what this is? This is actually an RFID 13.56 megahertz inductive antenna, or reader coil. It doesn't really radiate, so some people wouldn't call this an antenna, but a lot of people in the trade call it an antenna. And what it does is you send current around here, you make that beautiful H field solution that circulates around. And remember what you did in your previous homework, you solved the integral problem where you computed what is the H field at the center of this thing, and then how does it decrease as a function of distance away from the center, right? Given a dimension L and a distance Z away from along the Z axis, if this was centered at the origin, how does that field strength fall off? So I'll just go ahead and pass this around so that you can understand the geometry that we're talking about. This is just cheap FR4 circuit board. You can see the conductive path that goes all the way around. And this thing is a BNC connector, so you can connect it to a coaxial cable. That little twisty thing in there, the little yellow thing at the base, is actually a variable capacitor to help tune out the self-inductance. We'll see later why that's important in this kind of system. But this is basically the gist of it. I'll go ahead and pass it around. You can take a look at it. So that type of system, that type of antenna, or something very similar to it, is in all of those gray buzz card readers that you see around, that are used in security locks around campus. That's a 13.56 megahertz system. There's also a very similar circular one that's used down in the MARTA. Anybody rode the MARTA today to class? Yeah, you had those little swipe cards, right? Same thing. There's an inductive reader in there, and that is a circular coil, but it's a 13.56 megahertz card. Yeah?
Is the NFC the same thing?
The Nearfield Communications, that's it can be. That's kind of a buzzword nowadays that people are looking at for very short distances between, like, your cell phone and your vending machine or something. They think it's a good way to make electronic payments and the like. I can, if you want to get into true near-field communications.
It looks exactly the same thing on my phone as well.
Oh, is that an inset? I've actually never seen one on the phone before. Yeah. That could be either 13.56 megahertz or 125 kilohertz, depending on the, what technology that they've implemented. But it is very similar then. There's a reason why this is really good for payments, and it has to do with your homework problem. Oh yeah, you have a question?
Yeah, I haven't seen my phone as well. If you put a mark card up to it, it'll read it.
Oh, okay. So that verifies it. Yours is at 13.56 megahertz. Well, hey, let's take this description, this knowledge, back to our homework assignment here. And I had this solution posted. Let's get the overhead camera fired up, and I'll do a little bit of drawing on here too. So here's my solution. It's power versus range in a square loop. So that square loop problem that we could analytically solve as a function of the z-axis. And I'll draw here because I don't think this is showing up very well. My little graph is kind of drawn out. So I'll have to Sharpie it up. But this was the basic magnetic field solution that you should have come up with up there. And that's basically, you took the solution for the z component. All the other components are 0 because of symmetry of the problem. And the h field in the z direction for a single current leg, makes a component in the z direction. And then you just multiply that by 4, right? Because they're all the same size. It's a square. So it's basically you find the component due to 1, you multiply by 4, and you get the total field in the z direction. Everything else has to be 0 by symmetry. So that was a nice little problem. And you thought, oh, here goes Professor Durgan giving you one of these useless integrals again just to test your math ability, something you will never need in the real world again. Not true, not true. Because, and I think I just desecrated my slide with a permanent marker, but that's okay. That's okay. So this is the field strength, magnetic field along that z-axis. The power stored in a magnetic field is equal to the magnitude squared. We haven't talked about that yet. But basically the power available for coupling is magnitude squared of a field strength. So if I plot the magnitude squared of the magnetic field as a function of z, and I normalize that against, this should be a 0 here, so the center. So I go to the center here, I calculate the z component of h field, and that should be basically a maximum because I'm right in the middle of my coil. And as I move away, I should get a fall off. And that's exactly what I've shown here. So let me go ahead and darken this. Does that even show up? Sort of. It kind of just sweeps diagonally along here, which is a little deceptive because this is one length, L, one side of the square, away in distance. So this is at the center, 0. This is a distance L away from the coil. This tick mark here is 2L. This over here is 3L. So this is linear distance, moving it away from the coil. Over here, I've actually plotted this in the dB scale. So I've taken that quantity and plotted 10 log base 10 of that. So it goes from 0 dB, which is no loss from the center power, and it goes all the way down to negative 50 dB. That's 10 to the 5th. In fact, if you looked at it, the slope at this point, once you got past the L units, the slope through here is 1 over distance to the 6th in terms of available couplable power. The power in the magnetic field falls off 1 over distance to the 6th. So now you can see why this is so useful for near field payments, right? or MARTA card, or trying to read a MARTA card in a lane and not all the other adjacent lanes. Intrinsically, the mode of magnetic coupling is extremely lossy. If you double the distance, you incur 2 to the 6th loss. Double the distance, you get 1/64th of the power. So from going to L to 2L, that's 1/64th. 2L to 4L, that's another factor of 1/64. So there is a very tight bubble of operation that you can rely on in near-field communications, and this is why it's used for the electronic payments or the toll collections, for swipe cards, for buzz cards that are unlocking important buildings. You don't want somebody in the parking lot 30 feet away to accidentally open the door and have a hoodlum walk into the building. A hoodlum. Okay, so that's the basis of what we're doing. So now, how can we use that to communicate? How do all these tags and near-field communications and the like operate? And that's what today's lecture is going to be about. So we're going to take this result and we're going to do some mutual inductance. So here's our system. When I have two coils that are sharing flux, we electrically represent this system as a coil and another coil. And of course I'm going to put a voltage, and I got a current I1 going into the system. I've got a current I2 and a voltage going out of the system. And this is a coil, so it's going to have self-inductance L1. This is a coil. It's going to have self-inductance L2. This coil is the reader antenna that I'm passing around. This other coil is the thing in your smartphone. Or I got an example of an RFID tag that you can see a little bit clearly. I'll pass that around when it's time to. But these are coils that are sharing magnetic flux. And the one last thing to denote that sharing of flux in a circuit diagram, we put two dots on these inductors. And we denote that there's the sharing of flux with mutual inductance M. That also has units of henries. And it represents the amount of flux shared by the two inductors. Such that if you put a current into here and you make a magnetic field, and then you try to change that magnetic field, you're going to incite a voltage on the secondary coil. And that couples the system together. Yeah.
So is that kind of like a transformer, but it's got no like core going to it?
Yeah, exactly. A transformer in power engineering, if anybody's taken the power engineering class, is exactly this thing. The only difference is that M has a specific value. Usually in power, you don't want any what's called flux leakage. You want 100% of this flux to be shared with this flux. And that minimizes losses and maximizes power transfer. And so M takes a specific value in there. Let me define these. My inductance 1, based on the conversation that we had earlier in the week, that is basically the flux, magnetic flux, due to coil 1, traveling in coil 1, divided by the current that gave rise to that flux. Here I'm using a psi sub 1, as often EMAG books tend to do. Over here, in the second coil, of course, that also has a similarly defined inductance. The magnetic flux in the second coil divided by the current that gave rise to that magnetic flux. The mutual coupling, M, with units of henries, can be defined either of two ways. They are always equivalent due to the reciprocity theorem in electromagnetics. The flux in coil 2 due to the current in coil 1, or the flux in coil 1 due to the current in coil 2. And it turns out if the geometry is linear, these two quantities are always the same. if the instructor gets it right on the board. So, up until this we understand. These are inductors. Anybody that's taken the basic circuit theory class probably understands that. You have probably encountered mutual inductance far less. I'm not even sure if they get to it in time in the current circuits class. You may have seen it a little bit in power engineering. There is this thing called a coupling constant, K, which is the ratio of M, the mutual inductance, to the geometrical mean of the self-inductances in this system. K, it turns out, is always between 0 and 1. The reason why I bring this up is that 1 is the case of the power transformers. When you have a nice iron core that they're both of these coils are wrapped around and they're sharing all of the flux, you have darn near 100% coupling. And that's an ideal transformer. There's some additional assumptions that you can make when you analyze an ideal transformer that make it so very nice. But alas, in a realistic communication system like the one we're talking about, this is never going to be 1. This is probably going to be a small number, 0.1, 0.01, something down there. Because most of the flux of that original coil is circulating around and is not shared, does not pass through the little inductor coil of the tag. And that is unfortunate. But I will tell you, it's actually not that hard to analyze that situation. And that's what we'll go ahead and do from first principles. So what we're trying to do, the end goal of this class, is to take a system like this, and I'm going to put an arbitrary load here, and what I would like to get is the Thevenin equivalent of that entire system. Because once you get the Thevenin equivalent of that system, you've characterized the entire system, right? You can analyze this. If I say, oh, this system is behaving like this. So this is the beauty of electromagnetics. We're going to start with physics, and we're going to march it down so that you have a useful circuit model. And you can relate the physical parameters to the electrical parameters that you would put into SPICE or do your analysis with. Okay.
Dr. Durgan?
Oh, yes.
I've got a question about your symbol for magnetic flux.
Yes.
In our lecture on Tuesday, definition of inductance, you used a different symbol. Are they interchangeable, or does...
The one I use, unfortunately, the texts are very inconsistent with how they describe magnetic flux, and I think my notes kind of reflect that as well. So capital Phi, I think, is what was used in the last lecture, and I used a psi here. And it turns out that I think, depending on what book you're using, it's sort of 50-50 which one they'll actually pick. Sorry for not being consistent, but I think I've got a pair of notes that I made from a different text. Just, they are the same for all intents and purposes in this class.
Thanks.
Good question. Good question. Okay. Now, let's write the basic relationships here. Let's do this. Okay. I know from circuit theory that V sub 1, if I just have that inductance, self-inductance L1, V1 will equal to L di dt, and V2 will be equal to minus L2 di2 dt. Now notice that I have a negative side in front of here, and that's just because my I2, as I've defined it in that diagram, is flipped in polarity. It's coming out of the top of the inductor instead of going into the inductor. Right. If I define it the other way, I could put a plus there. But I don't want to do that because I want to attach something, a complex impedance, to the other side of that second terminal. And it'll be apparent why that's a useful thing to define it in this way when we get to that point. Now, of course, this is the self-inductance. By Faraday's law, if the current on number 2 coil is changing, it will incite a change in the first coil. And that's, of course, a very similar law. Mutual inductance di2 dt. And based on our polarity that we've chosen for current here, again, I have mutual inductance on the second voltage di1 dt. So the left-hand side of this is old hat for anybody that's taken a circuit theory class. The right-hand side, I'm just adding Faraday's law and reflecting the effect of coil 1 on coil 2 and coil 2 on coil 1. Now, the problem with that is that now these differential equations are coupled. I2 and I1 show up on both sides. If you try to incite a voltage in coil 2, that voltage will make a current, which actually reverse couples into coil 1, and you have this weird kind of cross dependency in the equations. So what I'm going to do, I'm going to convert this to the phasor domain. We're going to rearrange it, put it in acute matrix form, do some manipulations, and then we're going to back out what the Thevenin equivalent impedance is of this. And then everything will make sense. I will then pass around the tag, and everything will make sense. And you'll be able to model any type of system that uses inductive coupling. It's okay. Now, I want to go into the phasor domain because I need changes to get Faraday's law to work. We need to leave the world of magnetostatics and oscillate. If I just have a DC system, there's not going to be any coupling because the I's aren't going to change. Everything's zero. Now, the problem that you worked on your previous homework with the square loop was actually a DC problem. So you got an answer that was like HDC as a function of the z-axis observation, moving away from that coil. However, none of these systems actually work like that. They're always using AC current. And we can make a little assumption here. This is a bit of a cheat, but you can do it at low frequencies. The AC field is equal to the DC field times cosine 2 pi ft, whatever the frequency of excitation is, provided that that frequency is low. And when I say it is low, that means that the wavelength in free space corresponding to that frequency is very large compared to the structure of the coil. So let's do a quick order of magnitude calculation. Speed of light is 3 times 10 to the 8th meters per second. We said that these systems, like the MARTA tag, are operating at 13 megahertz, 13 times 10 to the 6th per second. What's the wavelength? Well, I'm going to cheat. I'm going to call this 10 to the 7th. So I don't like math. 30 meters. How big is that thing that I'm passing around? That's about 0.3 meters. It's about 100th of a wavelength. So if we were operating up at the UHF spectrum, like 130 megahertz, or if we were getting close to microwave frequencies, 1.3 gigahertz or 13 gigahertz, then the wavelength is so small you can't make this assumption. But we can get away with it at this frequency for these dimensions of problems. And so this is actually a well-known term in electromagnetics. This is called the quasi-static approximation. You analyze the system as if it was static, and then you slap a cosine on the end of it to reflect the fact that it's actually AC current. And it's an approximation, but for this system, it's a good approximation. Any questions with that so far?
What's the typical frequency range?
It all depends on the size. Yep. If you were to I wouldn't want to do this above 100 megahertz for that structure that I just passed around.
Why? Does it look like a DT at the extreme? I'm not understanding.
Well, what happens is at high frequencies, really high frequencies, the device starts to radiate, and you can just throw that little circuit model that I had over there out the window, because there are now modes of power leaving the device. It's almost like an extra impedance drawing power away, an extra resistance drawing real power out of the system. But it's not ohmic losses, it's radiated power. In this case, we don't have any radiated power. That's really the assumption that we're doing. And the reason is, this is just really just an inductive square. Power is circulating back and forth, sloshing back and forth with the sinusoidal field, but it is not radiating. And that's the key difference. Okay. So let's convert these equations that I put up here into the phasor domain, because ultimately that's what I want to do. We want a sinusoidal system. Okay. How do you convert a derivative into the phasor domain? What do you got to do? What?
Laplace transformation.
It's kind of like a Laplace transformation, yeah. But the nice thing about derivatives, or the phasor domain, is that the operation of differentiation with respect to time becomes multiplication, right? You just have to multiply by what? J omega. J omega. Or J2 pi f, if you're me. There's a dichotomy in electrical engineering, right? There's the J omega crowd. They're usually controls engineers or DSPers or whatever. And then there's like the RFE mag crowd, and they'd like to do J2 pi f. Truth be told, you should all be comfortable with either one. It's really easy to convert, right? But I always like the physical units of hertz, because that means something to me. If I said, oh yeah, this system, this RFID system, it's operating at 54 megaradians per second. What can you possibly do with that piece of information? Yeah, it sounds smart. Which is probably why the controls engineers do it, you know? No, I'm just kidding. Some of my best friends are controls engineers. Of course, most of them are on the right half plane, but... Oh, there's a joke that only one person laughed at. There's a funny joke. We'll see who actually has had a controls class. There was a plane leaving from Warsaw. Yeah. Have you heard this joke before?
Yeah.
Oh, okay. I won't tell it then. This is. Oh, okay. So there was a plane leaving from Warsaw to New York, and the captain midway, over Europe would be like, "Oh, look out the left-hand side of the plane, and there's Big Ben down in London." And everybody would get up and go over to the left-hand side of the plane, and they'd look out the window and say, "Oh, yeah, that's nice." And then when you got to New York, the captain said, "Oh, get up. On the right-hand side of the plane, you can see the Statue of Liberty." So all the Poles get up from Warsaw and go to the right-hand side of the plane, and the plane vanishes. Because you can't have Poles on the right-hand side of the plane. It's not possible. That's a really bad joke. But it's like the only controls joke I know. Okay. So let's convert this. Differentiation is J2 pi f L1 in the phasor domain. Here, we're differentiating again. So let's actually group this all together. I'm just multiplying everything by J2 pi f. And if you want to be really cool and be really elegant in your expression of this system, you could use a matrix. you could say V1, V2 column vector is equal to a matrix J2 pi f scalar times the matrix L1, L2 minus m plus m, operating on the quantities I1 and I2 vector. Oh, isn't that elegant? In fact, this type of system would allow you to analyze a crazy complicated inductive system with like 3, 4, 5, 10, 20 coils, all sharing inductance, stimulating currents on one another. Okay, so let's break it down now. We want to get that Thevenin equivalent impedance. So by definition, in the circuit that I just erased, my load voltage on output port 2, the ratio of that load voltage to the load current is going to depend on what you connect to it. In fact, the impedance of the thing you connect to it is that ratio, right? So to diagram this thing out, if I put an impedance here, Z2, or ZL, so let me be consistent with my notes here. We'll call it ZL. That's basically going to define the relationship between I2 and V2 on that port. Therefore, if I take this last equation, which says V2 is going to be equal to J2 pi f minus m times I1 minus L2 times I2, and I rearrange it so that I get V2 as a function of I2, or divided by I2 in terms of that. So what I wind up getting is J 2 pi f minus L2 minus m, the ratio of I1 over I2. So all I did was divide that second equation by I2 to get the ratio of V2 to I2. And by definition, this ratio must be equal to whatever device's impedance that I connected to it. Close bracket. That makes sense, right? Everybody following so far? Okay, so now let me rearrange it. And what I'm going to come up with is the ratio I1 over I2, solving in terms of those phasors. I'll put squiggles on them to denote their phasors. This is going to be equal to ZL plus J2 pi f L2 minus J 2 pi f m. Now, Thevenin equivalent impedance of the front side of that thing, if I go back to this diagram here, this is V1, voltage from here to here, and I define I1 as the current going through this device. It's the ratio of this voltage to this current that is the Thevenin equivalent impedance. So ZTH is equal to V1 over I1. Which, using the first equation, I can solve that as J 2 pi f L1 plus m I2 over I1. And from the previous equation, I already have an expression for this. If I just flip this and stick it in here, Now I have a Thevenin equivalent impedance expression that's only a function of M, L1, and L2. I've taken all the currents out of the equation. Only in terms of physical parameters of the system. So let me write the final answer, and we'll discuss. We'll put down the pencil and paper and discuss. What does it mean? So let's see. I've got there's going to be a J2 pi there. So when I distribute that out, I'm actually going to get a plus omega squared, or I should say 2 pi f squared, m squared, ZL plus J2 pi f L2. And let's put down the pencils and papers and talk about this result, because this is very important. How does this system behave? Okay, so imagine I got my tag up here. It's hovering above a reader, the antenna. It's sharing flux. The closer I bring this thing to the antenna, the square loop of current, the bigger M gets. The biggest M could possibly get is M squared could possibly get is L1 times L2, right? Based on our definition. But it's probably going to be a lot smaller than that, because there's no iron core that's conducting all the flux, 100% of the flux through this and this at the same time. But that's okay, because you can still do communications. So my Thevenin equivalent, as seen at the terminal here, at the input terminal, is going to be the self-inductance. Well, that makes sense. This is just acting like an inductor. So if there was no tag, we just ignore this part, right? But with the tag present, now I've got to worry about this term here. Now, before we go on, why is there a capacitor here? What's the point of this capacitor? I just modeled this straight up coil. Who said that?
Noise.
Reduce noise? Could potentially do that.
It wouldn't store the energy used to make the transfer. It gets discharged when it gets hit by the RFID.
Well, this is an alternating current situation. So really this capacitor looks like a minus J something. So if I got a good capacitor in here that's tuned to the inductance here, then exactly. What you're trying to do is make a minus J something that cancels out this term. If you do that, then the Thevenin equivalent impedance, as seen at the terminals here, right there, is just a function of the presence of the tag. Isn't that freaky? And the reason why you can do that is because we haven't modeled any resistance in here. As soon as you put some realistic resistance in here, there's some stuff that you can't cancel out in front that'll detract from the signal. But ideally, if you've got a really good conductor, even if the coupling is really crappy, the coupling coefficient is crappy and M is small, the only thing that will influence that coil is still this device. In fact, this is sort of the principle behind the MIT power experiments that were on YouTube like several years ago. Did anybody see those? I think there was a big coil, and then several meters away they were exciting a light bulb using inductive coupling. Yeah, this is very similar. You're just relying on the fact that even though they're not sharing much flux, the only power that you can way to expend power in an inductive system made out of really good conductors is through the coupling on the resonant device on the other side. But it has to resonate. And that gets us back to the second term here. So we put a nice capacitor. We tune it so that we cancel out this term. Now the Thevenin equivalent at that port is only due to this term. Depending on what I load my coil with here, This is the impedance of whatever chip that I splice in. Usually these are a coil of conductors, and the coil is kind of closed-circuited by a chip, an RF integrated circuit, RFIC. And that RFIC has several different types of electronics on it. The first thing it has is a charge pump, which basically rectifies and steps up the sinusoidal current. So in this system, you hit it with magnetic energy. The charge pump drinks up the magnetic energy, rectifies it, and pumps up a voltage level, a DC voltage level, so that it can turn on the rest of its logic circuitry. Logic circuitry wakes up. It says, oh, I am a MARTA card. You have ridden on this card 40 times, and there are, this was a 50 ride card or whatever. It basically is a bunch of ones and zeros. Ones represent rides, and you erase the ones every time you ride the MARTA. So there's how to ride for free, right? You just need an inductive system that you can program to put ones back in the system.
Oh, that's easy.
Yeah, that's pretty straightforward. You just need $20,000 worth of test and measurement equipment, and you can ride the MARTA for free. You'd have to ride it about 10,000 times to pay for it. Yeah?
Do you know anyone who could ROS that maybe $20,000 worth of equipment like maybe 10 minutes?
I don't know. I'm not advocating any illicit activity. I'm just making a comment. I'm not going to aid and abet anybody's criminal activities. So, okay. So your card wakes up. How does it get the information back to this port? Well, it switches in different loads. And if you just monitor the impedance here, the equivalent impedance here, you will see the chip as it changes this term. And it usually alternates between two states, or like an ohmic matched type of state that makes this purely resistive, and a short circuit, which makes this 0, or an open circuit, which makes this infinity. And in doing so, you have two different discrete values that you can monitor for the Thevenin equivalent impedance. Now, the one problem that you have with this system is that this term here is highly inductive, right? This is the self-inductance of the reader coil, or of the tag coil, excuse me. So it's a pretty large number because you took, in this case, I've got a card that has 6 windings. You loop around 6 times. Why do you want to loop around 6 times? Well, remember, you got to turn on diodes for that charge pump, so you want a high voltage. You care a little less about the current because you just, as you increase the voltage, you decrease the current in conservation of power, right? So you would rather have high voltage than high current. The CMOS devices don't take that much power, but they do take voltage to turn on, as well as the rectifying circuitry. So this thing here energizes itself, and it sees a lot of self-inductance because there are 6 windings here. It's a lot of mutual inductance. So this term is significant. What could we do on this tag to amplify the effect of changing Z sub L, the thing that we connected to the tag? Yeah, that's right. That's exactly right. It worked for over here. We put a capacitor that canceled this term out. Why can't we put it over here? So if you look at it, the true electrical model for all of these systems could be modeled with something like this. Variable capacitor. And of course, if you want to get realistic, there's some resistance here too. Call it R antenna. This will be C antenna. Mutual inductance, self-inductance number 1 of the reader. Self-inductance number 2. You'll get some tag resistance, R sub tag. And we'd like to have a variable capacitor in here. And our ZL is actually the impedance of the RFIC, which is the impedance of a charge pump when it is off and drinking up power, but when it has enough power to turn on, it is an open circuit or a short circuit or a resistive load, depending on what states you're switching between. So here's the next question. I can make this value C tag such that it cancels the series inductance there, right? And all I'm left with in that case, if everything goes well, then my ZTH, if we assume this is 0 or very, very small, and I look at my ZTH at that point, and everything resonates, then ZTH is just going to be 2 pi f quantity squared m squared over ZL. A little bit of change here will reflect through the system and give you a significant measurement at the terminals of the antenna. Yeah, Cameron.
You said the capacitor tag would cancel out the first inductance?
Yeah, that's right. So what we're saying here, well, yeah, this capacitance cancels out the self-inductance here, so that first term. And then what we're saying here is that we've got a minus J something term due to this capacitor, canceling out the self-inductance, J2 pi f L2 of the coil, so that these collectively are 0.
I think I missed something. Did you just, the resistance of the tag, did we just say that it was negligible?
Yeah,
It was
0.
small? Okay.
That's right. We did say that. So it actually becomes a pretty simple system once everything resonates out, right? This is a phasor. Now, a couple questions. We already know that as you increase the coupling, i.e. you bring this device closer to the antenna, M goes up and you get a better coupling in your system. Does this system work better at higher frequencies or lower frequencies? Think about it. I got f squared here. So generally, higher frequencies is better. It's better for coupling. It's better for Faraday's law. Higher frequencies change faster, and the voltage is going to be proportional to the rate of change of your magnetic field. So it only makes sense that going higher frequencies will cause bigger voltage excitations at the terminals of your loops through Faraday's law. There are other problems working with higher frequencies, though, because if you go too high, it starts to radiate power. Your system, at least from a coupling point of view, becomes less efficient.
There are more losses.
Yes, and there are more losses. Skin depth, for example. Your traces become more lossy as the currents kind of cling to the outside of the conductive path. So there's only you can only go so high before you can't play this game anymore of increasing the frequency. There's a good way to couple information, though. Okay, one last question about this system that I've drawn on the board. I've drawn a tunable tag capacitor. And I do have a capacitor on here. It's a parallel plate capacitor. You can see it because it's actually, they use the plastic substrate as the intervening dielectric between the two parallel plates, the insulating dielectric. And here's the problem with that. There's a aluminum stamped foil trace glued to the top, and another aluminum foil trace that actually has a yellow backing on it, so that's how you can turn it over and see that that's the capacitor. Two metal plates, cruddy stamped aluminum on a plastic substrate that doesn't have a lot of tolerance in terms of how it was manufactured. So if you just make your capacitor that way, you will get a variable result that's somewhat unpredictable and probably not the value that maximizes the communication through here. So how do you fix it? With a laser. So I will pass it around and you'll be able to, you'll have to put your glasses on and look very carefully. But before this thing left the factory, There's a strip of aluminum on one side, and then there's a strip of aluminum on the other side, and then the intervening plastic is in the plane of the board here. And we know from this class already that the capacitance of that system, C, is equal to area times epsilon over the separation distance. Epsilon of the plastic, area of this parallel plate looking down, and then the distance separating the backside plate from the top plate. Well, what you do, you have an automated tuner, because remember, these things have to be like 5 cents a piece or else they're worthless. They cost more than they add to the system. So you got to have an auto tuner, right? You can't have a person with a spectrum analyzer or network analyzer measuring these things as they come off the assembly line. They come off in these crazy big printable tape reels. So instead, you have an auto tuner that, depending on what the actual value of this over-designed capacitor is, it takes a laser beam and it cuts out a chunk, thereby reducing A to the value of the appropriate capacitance. So I'll go ahead and pass this around. I apologize to those in the video class, because I don't think there's any way you could see this if I put it under the camera. But sure enough, you can see a little chunk taken out of it, and that was done with a laser cutter and hooked in conjunction with an auto tuner circuit. What a beautiful electromagnetics problem this is. So any questions so far? Perfect understanding? Yeah, go ahead. Ryan.
Like, let's say you were really lazy and didn't want to get your RFID out of the car to open up the gate to your apartment complex.
Yeah.
How could you, I guess, essentially, I mean, you just have to increase the coupling enough to where it would, like, you know, how could you?
Yeah, how do you increase the coupling? So the question for the audience on video is, if you were lazy and you had an inductive system for your apartment, do you have an inductive system like this for the apartment? And you don't want to get out of your car to swipe your thing. You just want to, like, I don't know, wave it around like this. How do you get the thing to couple? Or maybe a more malevolent example is, if I wanted to sniff out the near-field communication transaction of, say, an electronic payment at a distance and steal someone's information, how would I do that? That's a related question. It is, and I'm not advocating doing that. I'm just saying this is how a bad person would do it. So, first of all, recognize that field strength, couplable field strength, falls off at 1 over distance to the 6th, right? So it's extraordinarily difficult to enhance the range of these links. And that's kind of by design. They're used for these kind of, we want a tight bubble type of system. However, there are some tricks. One, you could put some magnetic material inside the coil. And that is usually like a polymer with ground up iron components in it. Almost like, at that point, you're trying to make it look a little like a cruddy transformer. The magnetic material will conduct a little more magnetic flux, and you might get a little bit of range out of it. You could surreptitiously install a power amplifier on the reader so that the current is much bigger. But even then, you could multiply the current by a factor of 8, right? 8. And you would only double your range. In other words, power would go up by a factor of 64. Input power into the device, range would double. So that's probably not a very good way to do it either. You could put an active amplifier on your tag, and thereby make it, with a little coin cell and some clever electronics, you could make that Z sub L look bigger than it really is. Reflect more power that way. That's another way. That doesn't do good for the sniffing problem, because if you want to sniff at a distance, then usually you're limited by the signal to noise ratio, and if you put an amplifier on there, you wind up amplifying signal and noise commensurately. and then adding some extra noises in. So you never get any better. Here's a little experiment that I've always wanted to try to sniff malevolently Nearfield Communications transactions. Let's say somebody was at the countertop at McDonald's, and they were waving their fancy phone. It doesn't have to be McDonald's. It's just a restaurant of your choice. So here's your cash register. Here's the happy employee. And let's see, here's the near field antenna. And let's see, here's your phone. This is a very happy person because he has a near field communication phone. And so Flux is coming around here, but dying off 1 over r to the 6 as you go away from it. And you want to read, you have a laptop. You have a laptop that you are pretending to work at the restaurant while you are trying to sniff payments. And so you have a coil of your own with a very large aperture collecting flux, monitoring the transaction. And you've tuned it with capacitors so that it resonates at 13.56 megahertz. But it's too far away. So there's a little technique that I would advocate in this called the lily pad technique. And advocate if you wanted to be, which I'm not advocating you be. And that is, at a couple of the other tables, you hide resonant coils like this. So you short circuit this guy and then you tune it so it resonates at 13.56 megahertz. And then you put them under the table. And it turns out that 1 over r to the 6 coupling between the shorter distances is much less lossy than trying to do the whole thing. Kind of. If these are resonants, then that frequency bounces very well. And you can actually make the signal go a lot farther than you want. But you would have to hide them well, and you have to tune them very precisely. If you were a robber. Yeah.
If you're trying to make something that can generally read, like you don't know what the frequency is, but you're generally trying to read between the gap in frequencies. Like say I want to centralize all of my scanning devices to my phone or something.
Yeah.
Is there any way to do that without knowing the frequency for every single device you have?
Well, most of the devices that your phone connects to, this is actually a very narrowband device. So if you're doing this kind of near field coupling, it is only at 13.56 megahertz plus or minus a few kilohertz.
Right.
But if you're talking about, I've got a Bluetooth, I've got a wireless LAN, I got a cell phone frequency. Those are all. There's a broad band of much higher frequencies that you select, and that's a different mode of communication altogether. In this case, if this was being excited by really high frequency UHF or microwave frequencies, power would be radiated out, and you'd find that the power falls off 1 over r squared instead of 1 over r to the 6th. And so it can go a long way. It can cover an entire city block or an entire city if the power in the frequency is good.
Feasible, okay, so not a phone, but it's feasible to create a device. Like if I want my card scanned for my apartment and my buzz card and whatever other wireless scan device, I can create a device that I can use for all centralized scanning that can't really get broken into? Is it possible?
Yeah, you could do that.
Okay.
Like, could you copy on the spot and then just use that copy? Like let's say he has this.
Oh, yeah. Can you?
Easy with this. I'm lazy.
I'm sorry. I wasn't talking to you. No,
That's fine. That's fine.
No,
Okay.
so I'm saying like I'm saying if he has like a tag on him, like and I could touch it, then copy it, and then use it to.
Yeah, if there was no kind of encryption or security on that, you could read it, and then it would be fairly easy to make an emulator that would duplicate the presence of that device. I don't know how tightly encrypted.
Electronically or just physically?
Electronically.
Oh, okay.
Yeah. In fact, like a lot of these devices are encrypted, but the encryption is really crappy. Does anyone have an RFID enabled passport? It's the same kind of inductive system, and it has all of your information on the chip. And it's encrypted. It's encrypted. What they've taken is they've taken the words United States of America and exclusive OR'd it with the data.
Aren't all passports
Yes.
RFID?
Now the new ones are. They are.
Let's say I know credit cards, they're not even encrypted. You can read the data right off.
Yep.
RFID.
So if for example there was like a class full of knowledgeable electrical engineers that learned about this stuff, you could then wreak havoc with all the electronic payment systems in the world pretty easily.
It's not very safe.
No.
Why is it 13.56 megahertz? Why is that frequency?
Because there is the short of it. There are several discrete bands that you can use for what's called Part 15 unlicensed intentional emitters, and that happens to be one of them. It also happens to be high enough in frequency where you can get really good coupling, but you're not into these radiated modes and lossy electronics. It's kind of a sweet spot.
And there's also a cap in the power that you can emit, right?
That's right. So the FCC, the Federal Communications Commission, has a set of guidelines. If you want a device that's unlicensed, that's transmitting power, but you don't have to buy the license for it, then that device has to have a maximum free field strength and a maximum input power and some other parameters that it has to follow. And 13.56 megahertz is one of the frequencies you can use for that type of device. The government has allocated it as a free-for-all band for anybody that makes consumer electronic devices and certifies the device. Yeah?
Reddit through NFC of this, and then now I can just use my phone.
So can you program it and make it act like a MARTA card?
Yeah, I can.
Okay. And then you can ride as many times as you want for free?
I just saw his bar card information. I can just use.
See, you need to be able to not just read the information, but now you got to be able to write a bit to the prom.
It'll emulate the signal as well. So I can put my phone up to the Marty.
Okay. He's charging 75 cents a ride. It's a deal. It's a deal.
Do you have a ham radio license, or?
Ironically, no. I've never had the time to take the test. I just get my students to do it.
Yeah. Where do you go to do that here?
Amateur Radio Club, right across the hall.
Oh, really?
Yeah, literally go out of the door, right 20 feet, and then make another left at the Amateur Radio Club. And they've got all the manuals for studying for the test. They'll tell you when it's offered. Has anybody gotten their amateur radio license already? Anyone?
Already?
No? Yeah.
Is the NFC just making an interface with the reader, or is it also the mode of communication with the reader?
I don't know what's involved in the standard, but there's a whole bunch of protocol that kind of goes on top of this as well, right?
Okay.
Like how do you transmit the bits, how do you modulate them, how do you encode them, and that kind of thing. In fact, I don't think it uses straight up binary signaling, like switching between two states. State 1 represents a 1, state 0 represents a 0. It has some special symbols that it uses.
So pretty much it transfers all the information on the NFC to the reader. How would you reset it?
How would you reset what?
The reader.
How would you reset the reader?
Because if I made a payment, if someone wants to wanted to make a payment, how would you reset the reader so that it's not the same?
You know, I don't know. I don't know. I'm not knowledgeable enough with NFC payments to answer that. Any other questions? Well, we don't have enough time to start a new topic, so I will see you on Tuesday, where I think we'll do some magnetic materials. It'll